Unit Operations Control, Modern Heat Exchanger Control Strategies. Heat exchangers are critical components in thermal energy management across a wide range of industrial processes. Historically, their control strategies were rooted in classical PID regulation, using outlet temperature as the primary controlled variable. However, with growing emphasis on energy efficiency, process intensification, and tighter product specifications, modern heat exchanger control has evolved significantly. The integration of advanced instrumentation, modeling, and real-time data has transformed these systems into precision-controlled units capable of dynamic adaptation across varying loads and operating conditions. A core challenge in heat exchanger control arises from their inherently nonlinear behavior, especially when phase change, e.g. condensation or evaporation, is involved or when fouling affects heat transfer efficiency. In modern systems, control strategies now account for these dynamics by incorporating adaptive tuning algorithms that respond to shifts in gain and time constant. These algorithms leverage data-driven feedback to recalibrate control parameters in real time, maintaining stability and performance without operator intervention. Cascade control remains a foundational architecture, but has been enhanced by better inner-loop sensors and actuator feedback. In a typical configuration, the outer loop controls process fluid temperature, while the inner loop rapidly responds to utility flow changes. Advances in sensor technology have improved measurement resolution and response time, enabling more aggressive loop tuning and tighter temperature regulation. Additionally, equal percentage control valves, selected for their linearizing effect, are now often coupled with smart positioners that provide diagnostic feedback and ensure precise valve travel. Feed-forward control has gained greater traction in heat exchanger applications, particularly where disturbances such as fluctuating inlet temperatures or flow rates are measurable. These strategies use predictive logic to adjust utility inputs preemptively, improving disturbance rejection. When combined with feedback control, this hybrid approach significantly enhances robustness. Simulation tools integrated with control system software allow engineers to design and validate these strategies against dynamic load profiles before plant deployment. Digital twins have further revolutionized heat exchanger control. By creating real-time, model-based representations of the physical unit, operators can simulate the effects of fouling, bypass flow, or utility supply fluctuations. These models use first principles thermodynamics blended with machine learning to update performance predictions continuously. In this context, control systems can proactively compensate for degraded performance, initiate maintenance alerts, or recommend operational changes to maximize energy recovery. Thermal integration across process units has elevated the importance of coordinated heat exchanger control. For instance, in pinch-optimized systems, individual heat exchangers are part of a larger network where one unit's output influences another's input. In such configurations, local PID control is insufficient. Model predictive control (MPC) is increasingly applied to coordinate the actions of multiple exchangers, maintaining optimal temperature profiles across the system while respecting energy and process constraints. Instrumentation has also advanced. High-resolution temperature and pressure sensors with built-in diagnostics are now standard, and infrared sensors are occasionally deployed in high-fouling or hazardous environments. Wireless sensor networks offer flexibility in retrofits, particularly for large exchangers or remote systems. These networks feed into edge computing nodes that pre-process signals for latency-sensitive applications, ensuring fast loop performance even in distributed architectures. Safety and reliability in heat exchanger systems are also seeing new focus. Smart interlocks based on rate of change detection help prevent thermal shocks and tube failures during startup or load transitions. Some systems incorporate vibration and acoustic monitoring to detect early signs of mechanical wear, erosion, or leaks, conditions that would previously go unnoticed until significant degradation occurred. Integration with plant-wide optimization and control layers enables heat exchangers to participate in energy efficiency programs. Utility cost signals or production demands can be fed into supervisory control systems, which adjust exchanger operating targets to optimize plant economics. For example, utility steam may be substituted with waste heat recovery in real time, depending on current process priorities. Looking ahead, autonomous heat exchanger control systems are being developed with AI-enabled anomaly detection, self-learning set point optimization, and cloud-based performance benchmarking. These systems promise to minimize manual oversight while maintaining safe and efficient operation under all conditions. Together, these technologies mark a shift from reactive temperature correction to predictive, adaptive, and system-aware thermal management, making heat exchanger control a cornerstone of next-generation process automation. Unit Operations Control, Advanced VFD crude oil pump control for export operations. Crude oil export operations depend heavily on stable, efficient, and safe control of mainline pumping systems. Variable frequency drives, VFDs, have become the industry standard for controlling the speed and torque of large crude oil pumps due to their flexibility, energy savings, and ability to respond dynamically to fluctuating system demands. In modern export facilities, VFD-controlled pumps are critical in maintaining target flow rates, managing surge pressures, aligning with custody transfer conditions, and optimizing energy consumption, all under a digitally orchestrated control environment. Traditional fixed-speed pump systems required throttling via control valves to maintain pressure or flow set points, leading to significant energy losses and mechanical stress. VFDs address this by allowing the motor speed to match precisely the required hydraulic load. This is particularly beneficial in long-distance export pipelines where back pressure, temperature-induced viscosity changes, and terminal tank levels can shift continuously. By modulating the motor frequency, VFDs reduce power draw during low demand and ramp up smoothly during high flow periods, improving both operational stability and life cycle efficiency. Modern VFD pump control strategies are built around feedback from multiple process variables, such as export flow rate, pipeline pressure, tank levels, and valve positions. These signals are used to establish control loops where the VFD speed set point is calculated by a flow controller or pressure controller, often with override conditions based on safety or process constraints. The VFD acts as the final control element, adjusting pump RPMs to match system requirements. High-resolution sensors and fast-response PLCs ensure loop stability even under turbulent or high-inertia flow conditions. Dynamic pressure control is especially critical in crude export. Excess pressure can lead to line ruptures or unsafe conditions at receiving terminals, while under pressure can cause shutdowns or non-compliance with metering accuracy. Advanced control strategies now incorporate surge detection algorithms, pressure ramping functions, and soft start sequences to protect pipeline integrity. These functions are implemented in both the VFD firmware and supervisory control logic, allowing proactive intervention in pressure excursions and avoiding the need for relief valve actuation. Integration with pipeline modeling and real-time optimization platforms further enhances performance. By combining live flow and pressure data with hydraulic models, the control system can anticipate downstream disturbances, such as a tank switch, valve closure, or pigging operation, and adjust pump speed accordingly. Model predictive control, MPC, strategies are being applied in some export terminals to coordinate multiple pumps and stations in real time, achieving optimal line packing, reducing transients, and minimizing energy use. Energy efficiency is a key advantage of VFD-based systems. Rather than operating pumps at full speed continuously, power consumption scales roughly with the cube of the speed. Even small reductions in RPM can yield substantial energy savings. Modern VFD systems now support regenerative braking, which captures and returns energy during deceleration or shutdowns. Combined with power monitoring and analytics dashboards, operators can track real-time energy KPIs and align pump performance with sustainability goals. VFD control systems also contribute to better equipment longevity. By eliminating hard starts and abrupt load changes, they reduce mechanical stress on couplings, seals, and bearings. In conjunction with smart condition monitoring, vibration, temperature, and current signature analysis, pump health can be continuously assessed. Predictive maintenance algorithms can detect anomalies early, such as cavitation, impeller wear, or shaft misalignment, prompting targeted inspections rather than reactive shutdowns. From a safety and compliance perspective, VFD-controlled crude pumps are now integrated with safety instrumented systems, and emergency shutdown, ESD logic. Upon trigger conditions such as tank overfill, pipeline rupture detection, or fire scenarios, VFDs execute controlled deceleration and isolation sequences. Soft shutdown profiles avoid water hammer and pipeline collapse while bringing operations to a safe state. VFD fault diagnostics, e.g. overcurrent, phase imbalance, overtemperature, are fed into plant-wide alarms, enhancing visibility and response time. At the enterprise level, VFD systems now interface with SCADA, DCS, and digital twin platforms. Remote operators can adjust speed set points, override logic, or simulate operational changes with full visibility into pump behavior and energy profiles. With cloud connectivity and edge computing, advanced analytics, such as flow prediction, alarm trending, and energy benchmarking, can be performed in real time, supporting centralized decision-making and continuous performance improvement. The future of VFD pump control in oil export is converging with autonomous operations. AI-enhanced supervisory systems are being trialed to adjust VFD parameters in response to predictive models of flow demand, weather impacts on tankage, or upstream production forecasts. In this context, VFD crude pump systems are no longer isolated control loops, but are integral components in an interconnected, intelligent, and resilient oil export infrastructure. Unit operations control, intelligent three-phase crude oil separator control in modern operations. Three-phase separators are mission-critical in crude oil production facilities, tasked with efficiently separating oil, gas, and water streams before further processing, storage, or export. The control of these separators has evolved far beyond simple level and pressure regulation. Today, it encompasses smart instrumentation, advanced control algorithms, real-time analytics, and integration with upstream and downstream digital ecosystems. With increasing emphasis on production optimization, environmental compliance, and autonomous operations, modern separator control systems are engineered for precision, adaptability, and reliability across varying well conditions and fluid compositions. Traditional control approaches primarily relied on three independent control loops, one each for gas pressure, oil level, and water level, each manipulating its respective outlet valve or control element. While still foundational, this model has expanded to account for nonlinear process dynamics, compositional variability, foaming behavior, and slug flow effects. Control strategies now include multivariable coordination to ensure separation efficiency, maximize production uptime, and minimize manual intervention, especially important for unmanned or remotely monitored facilities. Advanced three-phase separator control integrates high-performance instrumentation such as guided wave radar, GWR, for interface level measurement, capacitance or microwave sensors for emulsion detection, and differential pressure sensors with built-in density compensation. These smart sensors provide more stable and accurate readings under challenging conditions like high-pressure gas, viscous emulsions, and changing temperature profiles. Sensor diagnostics and auto-calibration capabilities further improve measurement reliability over long operating cycles. Pressure control remains central to gas outlet management. Vented gas must meet pressure specifications for flare systems, gas compressors, or reinjection lines. PID-based pressure control loops are enhanced by surge protection logic and anti-slug algorithms, particularly in fields with inconsistent wellhead pressure or high gas-oil ratios. Some systems incorporate anticipatory logic based on upstream production data or real-time modeling, allowing pressure control valves, PCVs, or VFD-controlled compressors to react ahead of surges or drops, thereby preventing trips or flaring events. Oil and water levels are typically managed via cascade control structures. For example, the interface level controller for water may set a flow set point for a water dump valve controller, while the oil level controller governs the oil outlet valve. This approach decouples the fast-acting valve response from the slower-moving level signal, improving stability. In more complex separators, emulsion layers are detected and treated dynamically with automated chemical injection, heating, or interface rebalancing. These interventions are often linked to live diagnostics and fuzzy logic controllers that can recognize emulsion growth patterns and apply corrective action without operator input. Foaming, sand accumulation, and wax deposition introduce further complexities. AI-enabled pattern recognition is now used to detect foaming events via unusual level or pressure fluctuations, triggering anti-foam injection, gas flow modulation, or changes in separator pressure. Similarly, sand monitoring via acoustic or differential measurements can initiate separator draining or flushing sequences. These preventive control strategies reduce unplanned shutdowns and protect downstream equipment like pumps, heaters, and metering systems. From an optimization perspective, digital twin models of the separator allow control systems to simulate the impact of well behavior changes, fluid properties, or control set point shifts. This enables real-time tuning of interface levels, gas pressures, or residence times to optimize separation quality while maximizing throughput. These models can incorporate fluid dynamics, thermal profiles, and historical production data, providing a predictive edge over purely reactive control systems. In multipad or subsea production environments, centralized control of multiple separators is becoming common. Edge computing platforms process sensor and actuator data close to the equipment, execute control logic locally, and then transmit compressed data or alerts to centralized SCADA or DCS systems. This architecture reduces latency, improves fault resilience, and enables adaptive control strategies that adjust separator behavior based on field-wide optimization criteria. Cyber-physical integration is a growing requirement. Separator controls are tied into safety instrumented systems, SIS, enabling interlocks based on overpressure, high levels, or gas detection. Emergency shutdown, ESD sequences are intelligently staged, e.g., gas blowdown may be delayed until oil levels drop to avoid re-entrainment or carryover. Alarms are also now more intelligent, using alarm shelving, prioritization, and time-stamped causality mapping to reduce nuisance alerts and improve operator focus during upsets. Environmental compliance is another key driver of advanced separator control. Regulatory thresholds on flaring, venting, and produced water discharge require high-fidelity tracking of flows, compositions, and event logs. Modern systems include real-time mass balance calculations, leak detection, and anomaly diagnostics to ensure zero-waste targets are met. Integration with enterprise data platforms allows reporting dashboards to align production and compliance KPIs in a unified view. In the next-generation architecture, three-phase separator controls are becoming part of the autonomous production fabric. Reinforcement learning algorithms are being trained to optimize dump timing, pressure control, and chemical dosing without human oversight. The system continuously learns from field feedback, improving separation efficiency and uptime. As separators become smarter, they transition from passive equipment to active decision makers within the broader digital oil field, shaping how assets are managed, maintained, and monetized. Unit operations control, modern electrostatic desalter control for crude oil treatment. Electrostatic desalters are essential in upstream and midstream crude oil processing, responsible for removing inorganic salts, suspended solids, and residual water from crude before it enters downstream units like atmospheric distillation columns. The presence of salts, primarily calcium, magnesium, and sodium chlorides, can lead to corrosion, fouling, and catalyst deactivation in downstream units. As crude blends grow more variable and processing conditions more constrained, the control of electrostatic desalters has evolved into a sophisticated, multi-parameter operation involving emulsion management, electrostatic field control, chemical dosing, interface control, and real-time diagnostics. Traditionally, desalter control was focused on maintaining water wash ratios, interface levels, and electrostatic voltage within fixed set points. While this basic approach is still used in smaller facilities, it is insufficient in dynamic environments where crude API, conductivity, water content, and emulsifier load change rapidly. Today's desalter control strategies use a closed-loop approach that integrates inline analyzers, predictive models, and adaptive logic to optimize salt removal efficiency while minimizing chemical consumption, energy use, and oil undercarry. The core of desalter operation is the electrostatic coalescing field. Modern units employ high-voltage, low-current fields, typically in the 16 to 35 kilovolts range, to polarize and coalesce water droplets dispersed in crude. The coalesced water settles due to density difference, leaving dewatered crude overhead. Voltage control is now often adaptive. Based on crude conductivity, emulsion behavior, and interface stability, the system adjusts the field to maintain optimal droplet coalescence without risking electrical arcing or emulsion inversion. These voltage adjustments can be executed via PLC logic linked to real-time diagnostics, such as current leakage, spark detection, and dielectric profiling. Interface level control between oil and brine phases is increasingly handled by high-resolution guided wave radar, GWR, or dual interface capacitance probes. These sensors are more accurate than traditional displacers or DP transmitters, especially under foaming or emulsified conditions. Control loops maintain the oil-water interface within a safe and efficient separation zone, ensuring neither water upsets the downstream crude nor oil contaminates the brine. Cascaded control schemes, where the level controller sets a dump valve flow set point, allow tighter control, especially during feed transients. Wash water injection, critical for diluting and mobilizing salts, is no longer operated on fixed crude-to-water ratios. Instead, flow control is dynamically adjusted using conductivity meters on desalted crude and/or brine, inline salt analyzers, and process modeling. If downstream crude conductivity begins to drift above specification, the system can preemptively increase wash water or chemical dosage. Anti-surge control logic ensures that increased wash water does not overburden brine handling systems or destabilize the interface level. Chemical injection, particularly of demulsifiers and wetting agents, is now governed by adaptive dosing strategies. Rather than operating on manual or time-based set points, smart injection systems use real-time emulsion thickness trends, interface turbulence, and analyzer feedback to maintain optimal dosage. These systems can interface with emulsion scanners or dielectric profiling sensors that detect subtle shifts in emulsion stability across the vessel. By correlating emulsion growth with feed conditions and dosing history, the system can auto-tune dosage for the current crude slate. Temperature control plays a significant role in desalter performance. Higher crude temperatures reduce viscosity, improve water separation, and reduce emulsion stability. Modern systems incorporate crude preheat control into the desalter logic, adjusting heater duty or steam injection to maintain crude at optimal dewatering temperature, typically in the 120 to 150 degrees Celsius range. Integrated diagnostics ensure that crude does not exceed thresholds that risk vaporization, foaming, or destabilization of downstream heat integration. From a safety and reliability standpoint, electrostatic field protection has matured. Spark detection sensors, field harmonics monitors, and predictive insulation diagnostics alert operators before dielectric breakdown occurs. Automatic field shutdown and restart sequences are integrated with brine level alarms, pressure reliefs, and water carryover sensors. In advanced systems, digital twins simulate the desalter's electrical field behavior and flow patterns, enabling virtual testing of field configurations and preemptive mitigation of upset conditions. Environmental and operational efficiency have become parallel goals. Brine quality monitoring, using inline oil and water analyzers and TDS meters, feeds into automated brine recycle or disposal logic. In facilities with water reuse requirements, such as steam generation or reinjection, brine quality feedback is used to adjust separation and wash parameters in real time. This feedback loop helps minimize freshwater usage and reduce off-spec wastewater generation. Desalter control is also becoming increasingly integrated with upstream blending and downstream distillation control. In a model-based control framework, crude API, sulfur, salt content, and water cut are used to dynamically adjust desalter parameters to align with refinery corrosion targets and heat exchanger constraints. By coordinating desalter behavior with upstream blend predictions and downstream crude unit flexibility, the overall crude processing chain becomes more resilient and efficient. Looking forward, AI-powered desalter management systems are emerging. These platforms ingest historical performance, real-time sensor data, and operational context to predict the optimal combination of voltage, water rate, chemical dose, and dump frequency for each crude campaign. Combined with cloud dashboards and mobile interfaces, operations and maintenance teams gain unprecedented visibility into performance trends, alerts, and cost optimization opportunities, transforming the desalter from a passive protection unit to a proactive optimization asset.